Good afternoon and welcome to Chapter 11, Part 1 lecture. Today we're going to be talking about one-way ANOVA. ANOVA stands for Analysis of Variance. So here's the data we're going to be working with today. Actually, one thing I want to say before I talk about the data is one-way ANOVA is an extension of independent samples t-test. We use independent samples t-test to compare two groups, okay, on some sort of mean outcome variable. Okay? We use one-way ANOVA to compare two or more groups. So we're doing the or more, we're doing three groups today. We're comparing three groups on the outcome variable. So Mr. K thought room color would have an effect on reading comprehension scores. To test his hypothesis, he randomly assigned 5 students to take the reading comprehension test in rooms painted the following colors. So he randomly assigned 5 students to take the reading comprehension test in the blue room, 5 to take it in the red room, and 5 to take it in the yellow room. Okay, so step 1 is just like the independent samples t-test. We need to identify the IV, or independent variable. And once again, the IV is what varies among the groups of participants. So in this case, it's room color, right? Because some participants take the reading comprehension test in the blue room, others in the red room, and still others in the yellow room. And then LVL 1, 2, 3, it means level or group. So the levels of the independent variable, or the different colors, are going to be blue. Level 2 is going to be red. Level 3 is going to be yellow. So now we have the DV, or the dependent variable, and the dependent variable can also be thought as the outcome variable, or what everyone is measured on. So in this case, everyone is measured on reading comprehension. So it's reading comprehension score. Okay, so there you have step 1. Identify the independent variable, the levels of the independent variable, and then the dependent variable. I'm going to go ahead and keep on erasing the board as we go, just to keep it really clean. Okay, so I cleaned up the board a little bit. It seemed like there was a bit of a black film left over from last time. So let's go ahead and move on to step 2. So in step 2, we're going to identify the null as well as the alternative hypothesis. So again, this is exactly what we've done with the other inferential statistics we've learned about. Okay, so the null hypothesis here is saying essentially the population mean reading comprehension scores for those who take the reading comprehension test in the blue room is equal to the population mean reading comprehension score for those who take it in the red room is equal to the population mean reading comprehension score for those who take it in the yellow room. So that's one way to think about it, but probably a better way to think about it is this. The variability of the population mean reading comprehension scores among students in the blue, red, or yellow rooms is due to sampling fluctuation and not due to room color. Okay, variability means the differences that we see. Okay, so what would this look like? Okay, remember, we have to, in cases like this, we have to draw a picture to help us understand. So here's a population where the null hypothesis is true. Mu blue is equal to mu red is equal to mu yellow. So this is saying the variability of the population mean reading comprehension scores among students is due to sampling fluctuation and not due to room color. Okay? Before we talk about this, let's go ahead and find the average reading comprehension scores for our different rooms. So go ahead and calculate the averages right now. I'll go ahead and write them up there. The blue room has an average reading comprehension score of 6.8. The red room has an average reading comprehension score of 1.6. And the yellow room has an average reading comprehension score of 5.8. So this is the logic we have been using. We'll just do this. So if the null hypothesis is true, so all of the population mean reading comprehension scores among the rooms are equal, then obviously in our sample, they're not equal, right? So this is just saying 6.8 does not equal 1.6, does not equal 5.8, okay? So if the null hypothesis is true, remember, this is going to be due to sampling error or sampling fluctuation, right? As we sample from the population, we're going to get something around the null hypothesis value. So that's what this is saying. The variability of the population mean reading comprehension scores among students in the blue, red, or yellow rooms is due to sampling fluctuation and not due to room color. You might notice we need to change something. That's actually a mistake in the notes. That should say sample mean, right? The variability of the sample mean reading comprehension scores among students in the blue, red, or yellow room is due to sampling fluctuation and not due to room color. Okay? It would be due to room color if the differences we see here aren't due to sampling fluctuation. And therefore we would reject the null hypothesis. Good. I'm glad I found that. So in the notes this is wrong, something I have to change, but here you have it in the lecture, it's right. Okay. I'm going to go ahead and erase that. Actually, I won't for now. I'll go ahead and write the alternative hypothesis over here. Okay, so then we have the alternative hypothesis, and whereas the null hypothesis is saying the population mean reading comprehension score for those who take the reading comprehension test in the blue room is equal to the population mean reading comprehension score for those who take the test in a red room is equal to the population mean reading comprehension score for those who take it in the yellow room. Okay, so that's statement number one, which I didn't write on the board. Statement number two is saying the variability of the sample mean reading comprehension scores among students is due to sampling fluctuation and not due to room color. So due to sampling fluctuation, and then this is saying one or more population mean reading comprehension scores among rooms are different from the others. So the variability that we see in our sample data is not due to sampling fluctuation. Okay? So there you have it. I'm going to go ahead and erase step 2. So step 3, we're going to select our alpha level. Our alpha level is always going to be 0.05. Step 4, we're going to create a source table. And actually, this is something we definitely want to keep on the board, so I'm going to write it in the corner here. So this is step 5, our source table. So I'm just going to write it in the corner right here. So source, SS, degrees of freedom, MS, F. And we have a between source of variation, meaning there's variation between the groups, or rather among the groups, and then that's sometimes called treatment. So between, you may see it referred to as treatment. And then another source of variation is going to be variability within groups. And this is sometimes called error. Okay. Sorry, this was actually step 4. And we're going to leave step 4 on the board. And now we're going to do step 5 over here. In step 5, we're going to identify our different degrees of freedom. We have degrees of freedom between as k minus 1. We have degrees of freedom within, which is going to be n minus k. We have degrees of freedom total, which is going to be n minus 1. Okay, so degrees of freedom between, k represents groups. So we have what? We have 3 groups minus 1, so our degrees of freedom between would be 2. Okay, so once we figure that out, we have to add it to our source table. Degrees of freedom between is going to be 2. Let's do the next one, degrees of freedom within. What's our total n? Our total sample size. We have 5 per group. 5 plus 5 plus 5. So 5 for the blue room, 5 for the red, 5 for the yellow, so that's 15. 15 minus k, which is the number of groups, which is 3, so 15 minus 3, degrees of freedom within is going to be 12. The last one's going to be degrees of freedom total. It's going to be your total sample size again, which is 15 minus 1. So degrees of freedom total is going to be 14. So let's go ahead and put the within, and then we could go ahead and add total to the source table. Okay. You should notice something very important here. Your degrees of freedom between plus your degrees of freedom within are going to be equal to your degrees of freedom total. Okay, perfect. So we figured out our degrees of freedom. Now we're going to figure out our SS, or sums of squared. So our first one is going to be SS between is going to be the sum of NT multiplied by x bar t minus x bar gm squared. So that could be confusing. Let's just do it. Once you see it, you'll understand it. Okay. So NT. So again, this could be B technically because T stands for treatment or between. Okay, so there you have it. So this is going to be the sample size for the blue room, right? So it's going to be 5. And then the mean, right, x bar for the blue room, 6.8, minus the grand mean. Okay. So what we need to do to figure out the grand mean is to calculate the mean of means, essentially. So if you go ahead and you calculate the mean of means, you can say, okay, 6.8 plus 1.6 plus 5.8 divided by 3. So, and if you do that, you're going to get a grand mean. We'll call it GM of 4.73. So yeah, this grand mean, if you just add up 6.8, 1.6, and 5.8 and divide by 3, that's going to be called the unweighted mean. Okay? You could also calculate the weighted mean, and in the activity, I believe it's using the weighted mean. So let me show you that. It's technically more precise, because the weighted mean takes sample size into account. So you would just do this, in this case, 6.8 multiplied by 5, which is the sample size, plus 1.6 multiplied by 5, which is the sample size, plus 5.8 multiplied by 5, which is the sample size, and then divide by 5 plus 5 plus 5. Okay? So let's go ahead and solve that. Okay, so we have 6.8 times 5 is going to give you 34. And then 1.6 times 5 is going to give you 8. And then 5.8 multiplied by 5 is going to give you 29. So we have 34 plus 8 plus 29 divided by 5 plus 5 plus 5, so 15, is going to give you 4.73. Okay, so now think about it. Why do you think the unweighted mean and the weighted mean are equal in this case? The answer is staring you right in the face. It's because the sample sizes are equal. So when the sample sizes are equal, you could just go ahead and calculate the unweighted mean and get the same answer as the weighted mean. Check it out. Let's say the blue room had a sample size of, let's say the blue room had a sample size of 10. Okay? The red room had a sample size of 20, and the yellow room stayed the same. Let's go ahead and recalculate it. 6.8 times 10 is going to be 68, right? So this would now be 68. 1.6 times 20 would be 32. 5.8 times 5 would be 29. Okay? So 68 plus 32 plus 29. And then, of course, the sample size has changed here. So we have 10 plus 20 plus 5. So that's 10 plus 20 is 30 plus 5 is 35. Okay, so 28 plus 32 plus 29 is going to be 129 divided by 35. And we would get a weighted mean of 3.69. Okay, so for review, because the sample sizes are equal in this case, the weighted and the unweighted mean are the same. But in our hypothetical situation in red, where we changed the sample sizes, all of a sudden your weighted mean is now different from your unweighted mean. Okay? So like I said, I believe the activity uses the weighted mean. Okay. Anyway, so back to this equation. So 5 multiplied by 6.8 minus 4.73 squared. Okay? And so we have to basically, since it's between, we're doing this for every single group. There's 3 groups, we're doing it 3 times. So the first one's the blue room. So we did that, and now we have to add the next room. So the red room has a sample size of 5, a mean of 1.6, and a grand mean of 4.73. Okay, go ahead and square that. Then we have to do the same thing for the yellow room. The yellow room has a sample size of 5, a mean of 5.8, and then the grand mean, which is 4.73 squared. Okay? So what I need you to do now is subtract the numbers on the inside, square, and then multiply by 5. Go ahead and hold that number, and then do it for the next, okay? And then add them all together, and that's your answer. So what you should get, after you do that calculation, is you should get an SS between of approximately 76.13. And once again, when I did this calculation, I used a graphing calculator, and I saved every single decimal place along the way. What I recommend you do, if you don't have a graphing calculator and you don't know how to save values as you go, I recommend that you just round to 2 decimal places with every calculation. So you're going to get something close to this. Okay, so then we found our SS between. So go ahead and write that in as 76.13. The next one we're going to calculate is the SS within, or sums of squares within. Okay, once again, it's a little funky equation. Let me explain what we're doing. All we're going to do is we're going to take this value minus the mean squared plus 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 this value minus the mean of this group squared plus this. So all the way through. So this is a pretty long process. So let's go ahead and start with the blue room. So 8 minus the mean for that group, which is 6.8 squared, plus 9 minus the mean for that group squared, plus 1 minus the mean squared, plus 9 minus the mean squared, plus 7 minus the mean squared. So take a look. You see it? So every value in the blue distribution, minus the mean squared. And we do the same thing for the red room. One minus the mean squared plus 2 minus the mean squared plus 1 minus the mean squared plus 2 minus the mean squared plus 2 minus the mean squared. Okay? And then once more, we're going to do it for the yellow room. So 5 minus 5.8 squared plus 3 minus 5.8 squared plus 4 minus 5.8 squared plus 9 minus 5.8 squared plus 8 minus 5.8 squared. Okay? So we're going to do the same thing. So 8 minus the mean squared plus 9 minus the mean. So that's how you're going to do it. So go ahead and solve for the blue room first. Let me show you what I got. I got 44.8, so make sure you're getting that. For the red room, I got 1.2. For the yellow room, I got 26.8. Okay? So now, once you've come up with this sum for each of the groups, you just add those together. So 44.8 plus 1.2 plus 26.8 is going to give you 72.8. 72.8 is going to be your SS within. Okay? So there it is. I have to erase it. The last sums of squares we're going to be doing is going to be the total. So step 8, SS total. It's going to be the sum of x minus the grand mean squared. So what does that mean? We're taking each value, subtracting the grand mean, and then squaring it. 8 minus 4.73 squared, ... 7 minus 4.73 squared, plus 1 minus 4.73 squared, plus 2 minus 4.73 squared, ... 5 minus 4.73 squared. Okay, so again, we're going to be doing this 15 times. So 8 minus 4.73 squared plus 9 minus 4.73 squared plus 1 minus 4.73 squared plus 9 minus 4.73 squared plus 7 minus 4.73 squared plus, I'll change it to blue so you can see that there's a difference, or the group's changing. 1 minus 4.73 squared plus 2 minus 4.73 squared plus 1 minus 4.73 squared plus 2 minus 4.73 squared plus 2 minus 4.73 squared. Okay, so now the last group is going to be the yellow room. 5 minus 4.73 squared plus 3 minus 4.73 squared plus 4 minus 4.73 squared plus 9 minus 4.73 squared plus 8 minus 4.73 squared. Okay, so now it's a lot of work, but you could do it. So 8 minus 4.73 squared plus, so figure out what each of these values are and then add them all together, and I'm going to show you what you're going to get. You're going to get an SS total of 148.93 about. So let's go ahead and take a look at that. So the reason we calculate, sorry, that's a little close. I'm going to change the degrees of freedom color so it's not confused. So this was 14, this was 12, and this is 2. So we use total to check our degrees of freedom. We're going to use total to check our sums of squared between and sums of squared within. So check it out. 76.13 plus 72.8 is going to be 148.93. Excellent. Okay? If your total is equal to between plus within, it means you did it right. All right, good work. Let's keep on going. Step 9 is we are going to find our MS between, or MS treatment. So it says SS treatment, or SS between, divided by our degrees of freedom treatment, or degrees of freedom between, is going to equal our ms between. So all you're doing here, it's pretty simple. You're taking this red number, dividing it by this blue number, and you're getting your ms between. So if you divide those two, you're going to get, here, let me pull up my source table. When you divide those two, you're going to get 38.06 or 07. I'm going to write down 07. Okay? And there's one more relationship in this step. SS error, or SS within, divided by the degrees of freedom error, or the degrees of freedom within, will give you the MS error. Okay? So 72.8 divided by 12 is going to give you about 6.07. Okay, step 10. MS treatment divided by MS error is going to give you your F. Your F in this case is your inferential statistic. It's like the T that we have been talking about. So let's do it. So MS between, or MS treatment, is 38.07 divided by MS error, or MS within, is 6.07. And you're going to get an F of 6.27. So step 11, we're going to find our F critical value. So our F critical is very similar to our T critical, except with an F critical we have 2 degrees of freedom. We have degrees of freedom between and degrees of freedom within that we have to take into account. Okay? So again, F critical alpha 0.05 with 2 degrees of freedom between and 12 degrees of freedom within. So I wrote 2, 12. Okay, so let's go ahead and take a moment to look at this new table, okay? The F distribution.
So go ahead and open up Canvas, and let's go ahead and go to Files. Once you're under Files, just go to Tables and download the F table. So I already have it open here, so let's take a look. So there's 2 things about this table that you really need to pay attention to. Notice alpha level 0.05 is light face. This is light face. Bold face is alpha 0.01. So we're using alpha 0.05, so we're always going to be looking at the non-bolded numbers. Okay, so in order to find the T critical, we need to know the degrees of freedom between and the degrees of freedom within. So we know for this problem, our degrees of freedom between are 2 and our degrees of freedom within are 12. Okay, well, degrees of freedom for the numerator of the F ratio. What? Degrees of freedom for the denominator of the F ratio. So go ahead and take a look at the source table. Okay, in order to calculate your F, you have to take your MS between and divide it by your MS within. So what that's telling us is the numerator of the F ratio is between, okay, so this could also say degrees of freedom between, and the denominator of the F ratio is going to be within. Okay, so between in the columns, within in the rows. So we have 2 degrees of freedom between and 12 degrees of freedom within, right? So 2 degrees of freedom between, or numerator of the F ratio, and then 12 degrees of freedom within, the denominator of the F ratio. So we're not going to look at the bold number because that would be alpha 0.01. We're going to look at the light face number, which is going to be 3.88. So our F critical with 2 degrees of freedom between and 12 within is 3.88.
Okay, so we've figured out that our F critical is going to be 3.88. Now we could go ahead and draw a picture to figure out if we're going to reject or retain the null hypothesis. So something to know about F, it's kind of like half the t. The t can be a negative critical value and a positive critical value. An F can only be positive. So if you come up with a negative F, it means you did something wrong. So look, doesn't that look like half the t? Right? We're missing this other half over here, this negative portion. We just have this positive portion. Okay, so F critical is going to be 3.88. Then we're going to have our rejection region. P is less than 0.05. Reject the null hypothesis. And then we have P is greater than 0.05. Retain the null hypothesis. Okay? So let's go ahead and figure out where our F obtained fits on this rejection region, if you will. Okay, well, so the F critical is 3.88 and the F obtained is going to be 6.27. Okay? Okay, F obtained equals 6.27. So it's clearly in the rejection region, so we're going to reject the null hypothesis. P is less than 0.05. I'm going to go ahead and erase the source table. We're done with it. I'm going to go ahead and erase the entire board, right? You have these means in your notes. We're going to actually use them in a little bit. Okay, so the F obtained 6.27 is greater than the F critical alpha 0.05, 2 and 12 degrees of freedom, which we found to be 3.88. Therefore, P is less than 0.05. So we're going to reject the null hypothesis, and therefore we're going to interpret the alternative hypothesis. And we're going to say that one or more of the population mean reading comprehension scores among rooms are different from the others. So the variability is not due to sampling fluctuation. It's due to the fact that room color does significantly have an impact on reading comprehension scores. Okay. We just have a couple more interpretations to do. I'm going to get another red pen. Make sure it's really clear for you all. That one's not that good either. Let's see. That seems to be better. Okay. So the probability of the actual data obtained. So seeing that sample mean variation that we saw, right? Blue 6.8, red 1.6, yellow 5.8. If the null hypothesis is true, the null hypothesis is saying all the population reading comprehension scores among rooms are equal is less than 5%. Okay, so it's just like the picture we drew earlier. The null hypothesis, mu blue equals mu red equals mu yellow. What we got 6.8 is not equal to 1.6 is not equal to 5.8. So the probability of getting the sample means that we got, if the null hypothesis is true, is less than 5%. Because of the small probability, p is less than 0.05, it is concluded that the mean variability of the population from which the sample was drawn is not the mean variability specified by the null hypothesis. Okay? The sample mean variability did not occur by chance in a population where the null hypothesis is true. So it's not a chance fluctuation. Once again, if this was due to sampling error that we got what we got in our sample, okay, then it would be a chance fluctuation. Okay? And the probability of getting a chance fluctuation, p is greater than 0.05. But because we got what we got and the probability of that is less than 0.05, we're going to argue that this isn't our population. The null hypothesis does not represent the population from which we drew our sample and got our sample values. Okay? We're saying it's going to be something closer to the variation we got. So maybe they're not all equal. Maybe this red line should be the population value. Again, this is the same logic that we use for t-test to test the difference between row and zero. One sample t-test, independent samples t-test, dependent samples t-test. And now we're on one-way ANOVA. This logic is identical. Okay, good. I think we're good there. So one thing I want to do before I erase the entire board, like I did last time, and then I had to write it all up again, is I want to go ahead and show you what this would look like if we retain the null hypothesis instead of rejecting the null hypothesis. So let's say our F obtained was just a 1. Okay, so obviously that's going to be less than our F critical, so our P is going to be greater than 0.05. We're going to retain the null hypothesis, and therefore, in lieu of interpreting the alternative hypothesis, we're going to interpret the null hypothesis. So this now just becomes a copy and paste of the null hypothesis. We're going to change this to room color does not significantly affect reading comprehension scores. The probability of the actual data obtained, so the sample mean variability that we see, and obviously if we're retaining the null hypothesis, our sample mean variability would be much different. The values would be closer to one another. So let's say hypothetically they were actually 2, 3, and 4. Okay? So the probability of the actual data obtained if the null hypothesis is true is greater than 5%. Because of this large probability, p is greater than 0.05, it is concluded that the mean variability of the population from which the sample was drawn may be the mean variability specified by the null hypothesis. the sample mean variability occurred by chance in a population where the null hypothesis is true. And then this little writing I have here is going to say it is a chance fluctuation. Okay, so there you have it. That's what it would look like if you retain the null hypothesis and then you'd stop. You're done. But you didn't retain the null hypothesis. You rejected the null hypothesis. So I'm going to go ahead and erase the board, and then we're going to take our next step. Okay, so we rejected the null hypothesis. We know that room color has a significant impact on reading comprehension scores, but all that one-way ANOVA is going to tell us is there's a significant difference somewhere between or among the different means. In order to figure out where the differences are, we have to do something called Tukey's HSD. And that is step 13. Step 13, Tukey's HSD. And what HSD stands for, in case you're interested, and maybe you're not, it stands for honest, significant difference. So here are your different, here's your equation for Tukey's HSD. Just write it under. So here's your equation, and we have to do a total of 3 comparisons because there are 3 groups. We have to compare the blue room to the red room, the blue room to the yellow room, and the red room to the yellow room. So blue versus red. Okay, so you can flip-flop the means if you want. It's just going to have an impact on your interpretation. So in my notes, I put the mean for the blue room first, right? So go back to your notes. You have the means for all the rooms. The mean for the blue room, 6.8. 6.8 minus the mean for the red room, which is 1.6, divided by the square root of your MS error. So go back to your source table to figure out your MS error. It's going to be 6.07 divided by 2, multiplied by 1 divided by 5 plus 1 divided by 5. Okay, so one thing you might be noticing is the MS error is going to be the same for all the groups, and all the groups have 5. Okay, so the denominator for all these comparisons that we're doing are going to be equal. But realize, once your sample sizes switch, like let's say one group has 10, another one has 20, that's no longer going to be the case. Okay. Let's do the blue versus the yellow room. So the blue room, once again, is 6.8 minus the yellow room, which is 5.8, divided by the square root of, it's going to be exactly the same as the denominator of the equation above. 6.07 divided by 2, multiplied by 1/5 plus 1/5. Okay, the last one is going to be red versus yellow. Okay, the mean for the red room is 1.6. For the yellow room is 5.8. Again, the denominator is identical, 6.07 divided by 2, multiplied by 1/5 plus 1/5. Well, let's go ahead and solve these. So what I want you to do is go ahead and solve this first. 1/5 plus 1/5, okay? So do that, 1/5 plus 1/5. I'll write it down. I'll write it down for you. Let's do it. Okay. So 1/5 plus 1/5 is going to be 0.4. So this is going to be 0.4. And then 6.07 divided by 2 is going to be 3.035. So multiply that by 0.4. And then you're going to take the square root of 1.214. And you're going to get for the denominator 1.10. Okay, so what's awesome for this problem, because like I said, the sample sizes are identical. Okay, each group has 5. The denominator for each equation is going to be 1.10. That's exciting. Okay, so the denominator for all the equations are going to be 1.10. So then all you have to do is subtract the two means and divide by 1.10. So I'll go ahead and write the results. So blue versus red, you're going to get an HSD obtained of 4.72. For blue versus yellow, you're going to get a HSD obtained of 0.91. And for red versus yellow, you're going to get an HSD obtained of negative 3.82. Okay, great. So what are we doing here? The next thing we have to do is we have to find the HSD critical. So HSD critical, we're going to have our alpha equal to 0.05. But we're going to use our levels of the IV and our DF within. Okay? So HSD critical alpha 0.05. How many levels of the independent variable do we have? How many groups do we have? We have 3 groups. So 3 and then degrees of freedom within. Go back to your source table and we have 12. Okay, so now time to learn about a new table. Okay, so let's take this moment to look at the HSD table and figure out our HSD critical.
Okay, let's go ahead and find the HSD critical. Now to find the HSD critical, go ahead and log on to Canvas, go to Files, and when you're under Files, go ahead and go to Tables, and you want to download the Tukey table. Okay, so I already have it over here. So when you download it, notice that one table is alpha 0.05, and the other table, one table is alpha 0.01, and the other table is alpha 0.05. So obviously our alpha is 0.05, so we're going to go ahead and make sure we use this table. Okay, number of levels of the independent variable. So we have determined that there were 3 levels of the independent variable. Just go back to step 1 of the one-way ANOVA, and you'll see that there's 3 levels of the independent variable. The blue room, the red room, and the yellow room. Okay, so we're 3 levels of the independent variable, and there are 12 degrees of freedom within. So 3 and 12, right? So there we have it. Okay, our HSD critical is 3.77.
Okay, cool. So we figured out that our HSD critical is 3.77. So essentially what's going on here, this is going to look exactly like a independent samples t-test. So, right, comparing 2 groups. This is basically independent sample t-test, independent samples t-test, independent samples t-test. So check it out. So it's like you're going to have this rejection region. You're going to have your HSD crit as a negative 3.77. and you're going to have your HSD crit as a positive 3.77. Okay, so P is less than 0.05. Reject the null. Okay, remember the null is saying there's no difference. They're equal in the population. Okay? Okay, in the center, P is greater than 0.05, retain the null. Alright, check it out. Blue versus red, we have an HSD obtained of 4.72. 4.72 is in the rejection region. Okay, so we're writing P is less than 0.05, and I'm just going to write, yes, there is a significant difference between these two groups in the population. Okay, and then 0.91 is going to miss. 0.91 is going to be in the retain region. P is greater than 0.05. No, there is not a significant difference between these two groups in the population. Negative 3.82. It's going to just make it. Okay, P is less than 0.05. Yes, there is a significant difference between these two room colors on reading comprehension score in the population. So there you have it. This is like a shortcut method. And we figured there's a significant difference between reading comprehension scores if you take the reading comprehension tests in the blue room versus the red room. Okay, since there's a significant difference, we go back to the sample data and we say, if you take the reading comprehension test in the blue room, you do significantly better than if you take the reading comprehension test in the red room. Okay? 6.8 in the blue room, 1.6 in the red room. Our other significant differences between the red and the yellow room. Okay? There's a significant difference. Go back to the sample data. Okay? It looks like if you take the reading comprehension test in the yellow room, you do significantly better on it than if you take it in the red room. Okay, yellow room being a reading comprehension score of 5.8, red room a reading comprehension score of 1.6. Okay, there you have it. I'm going to go ahead and erase this and then do an interpretation that is going to say exactly what I just told you. Okay, students who took the reading comprehension test in the red room did significantly worse. You know what I'm going to do? I'm going to go ahead and move this over here. Seems like it feels out of place. So mean for the red room is 1.6. So students who took the reading comprehension test in the red room, mean of 1.6, did significantly worse than students who took the reading comprehension test in the blue room, okay, mean 6.8, and the yellow room, mean is 5.8. There is not a significant difference between the blue room and the yellow room on reading comprehension scores. Okay, so there's the formal interpretation. So we found differences. Now we can make a statement about the size of the difference using effect size. D equals x bar 1 minus x bar 2 divided by the square root, that's going to work out better, of ms error. Okay. So we have blue versus red, right? And I'm just going to do this with the significant findings, but you could actually do it with the non-significant findings as well. It will give you information about the degree of the difference that was not significantly different. So the mean for blue is 6.8 minus the mean for red, which is 1.6. Square root, ms error is 6.07. Okay? Take the square root of 6.07 and then take 6.8 minus 1.6 divided by that, and you're going to get a D of 2.11. Now let's look at the yellow room versus the red room. D equals 5.8 minus 1.6 divided by the square root of 6.07. Okay, you know what to do. Go ahead and do that. You're going to get a D of 1.70. Let me go ahead and write the interpretations. Okay, so before we get into the interpretations, remember for D that a 0.2 is small, a 0.5 is medium, and a 0.8 is large. Okay, so the effect size for the blue versus the red room is 2.11. There is a very large difference between reading comprehension sample mean scores for students who took the test in a blue room and those who took the test in a red room. Okay, so there's a very large difference between these two groups, okay, on reading comprehension score. And then for the yellow versus red room, D equals 1.7. There's a very large difference between reading comprehension sample mean scores for students who took the test in a yellow room and those who took the test in a red room. Okay, so that's effect size for you. Okay, we went through all that to find that there's a significant difference in the population between those who take the reading comprehension test, okay, in blue rooms versus red rooms and yellow rooms versus red rooms, to the point that it seems like choosing to paint the room blue or yellow is going to be related to better reading comprehension scores as compared to painting the room red. Okay, so there you have it. We're all done for now. So let's go ahead and pray. Dear Heavenly Father, once again, wow, it's amazing that we have the strength to do this, Lord. Your work is evident in the students' performance. They are just doing so great. They are just sticking with it and just going for it, Lord. Thank you so much for these wonderful students, Lord. Thank you so much for giving us this beautiful opportunity to talk about statistics. Thank you for creating statistics, Lord. Give us the wisdom to turn to you as we complete this class and to ask you, Lord, okay, here's this class that you put me into. How am I going to use it to relate to my career? How am I going to use it to do your work for your kingdom? Lord, we just praise you always and always. We are in so much awe. Thank you for everything. In Jesus' name we pray, amen. Thank you. Be sure to let me know if you have any questions. Have a nice evening.